Hello again, everyone. This is Tutorial 6 for Comp526. We're continuing with subproblem 6, 7, and 8 for this video. So let's get right to it. So the next exercise is to construct the LCP array. Now, in order to do that, we need our suffix array. Okay, so here I have my suffix array. Now, in order to find the LCP array fast, what we do is we take our suffix array. I want to remind you this suffix array has these suffixes here. Basically, value 8 here means that this is this suffix here. Value 7 is this suffix here. Since we start from 1 instead of 0, we have to add 1 whenever we see a value. So value 8 here is actually value 9 there, so it's this suffix. I have listed it here. For value 7, go to 8, $8, I list it here. Value 6 is 7 here, $8, I list it here. And I do all of them like this. So I list each suffix here. Now, to compute the LCP, what I do is I check the adjacent suffixes and see how many of their prefixes match. So yes, LCP stands for least common prefix. So for example, this, in order to find the first value, I compare how many common prefixes those two suffixes have. Now they have 0 common because this is a dollar, starts with a dollar, and this starts with an A. So I have 0 here. For the next one, I compare these two. So $8, $8, they only share one common. Let me put this here. So they only share one common character. So here, for their prefix, so here I add a 1. This is better, I think. Next one, so here I have $8 and then ABB and so on. Again, here they share one common character, so I mark it like this. So here I put value 1 in my LCP. Next one here, they share A, B, B, and A, and then we have a mismatch, so they share four different one for a prefix of length 4. Here I put a 4. Next one, A and B are different, so here I put 0, no common prefix. Here, B, B, A, A, so 2 common characters for the prefix. Put a 2. And B, B, A, B mismatch, so common prefix of length 1. Then B, 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 A, A, so 3 of them. Oops, sorry. So 3 common characters. And the last one, we don't need to compare it with anything. So this is how we create our LCP. Now the reason why this works is because the suffix array here has all of our suffixes listed in lexicographical order. As you can see, first we have the suffix that starts with a dollar. After that we have all of the suffixes that starts with an A, then the suffix that starts with a B. In the second line, for those suffixes that share the first character, they have the same first character, then again they are sorted lexicographically. So all of the suffixes that start with an A are listed in lexicographically here for the second line, $A, B, B. The same for those starting with B. So all of the words are listed all of the texts are listed lexicographically. This is why when I check for longest common prefixes, when I'm checking for this thing here, let's say I'm checking this suffix here, $, if there is some other suffix that shares the longest common prefix with it, it will be exactly next to it. Since they are listed lexicographically, it's not possible for it to be listed somewhere here, for example, because if it started with an A, then it would be somewhere here, close to it. And that is why this thing works. So we'll move on to exercise 7 afterwards. So exercise 7, oops, sorry, these are the solutions. Here it asks to annotate the internal nodes in the suffix tree with their string depth. We have already done it for subproblem 3. It looks like that. And explain the connection between string depths and the LCP array. So let me check. So here we have the LCP array, and here we have the string depths on the internal nodes. Now, what is common between those is that if you I remind you here that in order to compute value 0, what we did is we computed the longest common prefix between the two adjacent leaves. So between leaves 8 and 7 here, we computed what's the longest common prefix between the two. Now, this value is exactly the same as the string depth of the least common ancestor between 8 and 7. So 8 and 7, their common ancestor, if we go up, is number 0. Both of them, if you go up, meet at, this is the first point where they meet. Let's say they traversed upwards. This is their least common ancestor. And the value 0 here, which is the string depth of this internal node, is the same as the LCP value here. Let's check the next one now. Now between 7 and 6, their least common ancestor, as you can see, is number 1 here. And we also have value 1 at the LCP array. And for 6 and 3, their least common ancestor is again 1. This is where they meet for the first time if they traversed upwards. And here we have value 1 again. 3, 0, least common ancestor is 4, same as this. 0 and 5, least common ancestor is 0, as here. 5 and 2, least common ancestor is 2. Sorry. When I say 2, 1, and so on, I mean the string depths of the internal nodes. So the string depth of their ancestor is 2, as here. 2 and 4, this is their least common ancestor, has a string depth of 1, like here. And 4 and 1, least common ancestor is this one here, has string depth of 2, 3, same as this one. So the values here are the same as the least common ancestor, the string depth of the least common ancestor of the leaves. And this is the relation between the LCP array and the least common ancestors of the leaves here. Next we'll move on to exercise 8. So for exercise 8, we need to use the above structures to find the longest repeated substring in T. Now that is quite easy to do. What we do is we go to our longest common prefix array. We find the longest value, that is number 4. So this is the longest common prefix between leaves 3 and 6 here. So we go to leaves 3 and 6. It's easier to see here. So leaves 3 and 6, if we go here, it's those two. So their longest common ancestor is 1. And am I mistaken somewhere? Yeah, sorry. Let's take it from the beginning. Sorry. This value 4 here, it's not between 6 and 3, it's between 3 and 0. My bad. This is what is the longest common prefix between this suffix and this suffix, which is 4, because this is the longest common prefix they share. So we go to those two, 3 and 0. Their least common ancestor is 4. So what we need to check is what are the string depth here is 4. So we can check that the longest common substring is this exactly, A, B, B, A. So we don't even necessarily have to go back here since we had this nice little example there. But if you wanted to check, you would have to go back to 4 and check what is the longest common prefix here. What is the prefix here, which would also be the longest common substring in of the suffixes in T. It would be probably easier to see here. So this is 3, this is 0, this is their ancestor, and you can see that for us to get there from the root, we go through A, B, B, A, which is again the same longest common substring in T. And that finishes exercise 8. I'll see you next week.